This time, we're going to talk about Fourier transform and Fourier space, which is a very important concept in understanding microscopy. Well, Fourier transform is all about math, like here. So I'm going to make it simple. Let's start with a simple sine wave. As simple as possible, you see sine oscillation, very smooth oscillations. To describe this sine wave, well, you have to have some mathematical formula. Like here, as simple as it can go, I, which is intensity at a certain point, equals sine of the coordinate x. And there are more properties to this wave. For example, you can have different spacing or different frequencies. And in this case, you can see 3 white strips in the entire field of view. We can say it has a frequency of 3. And in the case when you have a frequency of 4, k equals 4, you have 4 white strips. And higher frequency, k equals 6, and even higher frequency case, when you have k equals 30, then there's lots of white strips in here. Very dense, high frequency waves. So that's one aspect of a pure sine wave. Now, in addition to frequency, there's also another thing, which is the amplitude. Now you have a coefficient a in front of the sine function. And in this case, you have amplitude of 1. And when you have amplitude 0.5, it's dimmer, or smaller oscillations. And amplitude of 0.25 is going to be even dimmer of the image, or even lower contrast. That's now 2 of the properties of the sine wave, the frequency and the amplitude. Getting a little bit more complicated, we have an additional phase factor in this sine function. You can see here is one additional phi in the bracket of the sine function. And in this case, this phase is 0. That means the sine oscillation here starts from 0 and continue oscillating. If we have an additional phase shift of 45 degrees, and you can see the entire wave get translated, and it starts somewhere midway. And we can have more phase shift, like 90 degrees, 135, 180, 225, 270, 315, until we get a phase shift at 360 degrees. That's one entire circle, so it's come back to the original sine wave. This is the phase factor. And a fourth one we need to consider is that we're describing a 2-dimensional image. In this case, the sine wave function is basically oscillating along the x direction. It can oscillate along an axis that's slightly off from x direction. And in this case, we have to have a little bit more complicated math to describe it. And you can see in the sine function here, we changed both the k and x into 2 vectors. And then k essentially describes as a vector, and the k as a vector now essentially describes the propagation function of this sine wave. So we have our x and the y-axis, and we have a vector of k. And in this case, the k has a 30-degree angle to the x-axis, and that is the propagation angle. And in a different case, this vector has been rotated to have a 60-degree angle to the x-axis, and you can see the entire waveform gets rotated. So that are the 4 parameters to describe a 2-dimensional sine wave. And we have our frequency, and we have our orientation. Both of these are included in this k vector. And then we have our amplitude in A. We have our phase in the phi 0. We need to find a graphical way of describing these sine functions, because looking at the mathematical formula and looking at pure numbers, that's very boring. Then we can have our coordinate system. And in this case, to avoid confusion, I called it kx and ky instead of x and y, but it's basically the same thing. And then we have a k vector. Just now, I say the orientation or the direction of the k vector tells the propagation direction of the sine wave. And in fact, the length of this k vector, the wave vector, tells the frequency. And so the k describes the frequency and orientation as a vector. For each point on this 2-dimensional kx, ky plane, we can have 2 values. One value is a, as a function of the k vector that tells the amplitude of the sine wave, and another value is phi that tells the phase of the sine wave. So a total of 4 numbers describes this sine wave. And then, because we're looking at a 2D plane, you can draw them, plot them into a picture. And this is basically a full picture of describing a lot of different sine waves. Each point on this picture describes one sine wave with a certain frequency and orientation, and the value of this point describes the amplitude and the phase. And that is how we can graphically represent a collection of different sine waves. So far we're talking about simple sine waves. But whatever cell structure we're looking at, they are not sine waves. They have fairly complicated structure. And how can we use sine waves to describe the structure? Well, again, we started with an extremely simple example. Now, instead of sine waves, we have black and white strips. That's simple enough. But even that differs significantly from a pure sine wave. Just plot cross-section, you can see that the sine wave is a fairly smooth oscillation. But here, now we have very sharp steps. We can try to compensate for that, though. For example, here at the edge, this sine wave has a smooth drop, whereas this black and white pattern has a very sharp transition. So we can imagine if we have yet another peak here, and that will somewhat compensate for this. And at the same time, if we have a negative peak in the middle, that will also compensate for this peaky behavior of the sine wave to make it more flat. So this is what we do. We have yet another sine wave, which is 3 times the frequency. And sum them up. You can see, because it's 3 times the frequency, and it has a negative peak in the middle and 2 positive peaks at the edge, and that make this overall shape more step-like. But this is still not perfect yet. We can consider more. Further compensating for it, this time we have another one 5 times the frequency. And when we have an infinite amount of these adding up, then we will approximate our black and white strip pattern. So this is the process of how we can use a collection of sine waves or collection of different spatial frequencies to describe a real image. And we can write it in mathematical form, and this is important. As well, our original image, fx, equals the sum of different sine functions. And then the gx actually describes the amplitude and the phase of these sine functions, how they are summed. So now we have 2 functions. One function is fx that describes the real image in the coordinate x. The other function is gk that describes our collection of sine waves that's going to sum up into this fx function. That's in the coordinate of kx. If you look at this image, you can see discrete spots. The position of these spots describes the spatial frequency. K equals 1, 3, 5, and very dim 7, and there can be infinite number of them. And the intensity of this spot essentially describes the amplitude. In this case, we're not considering the phase shift yet. So in this case, you can see that we have some relationship between fx and gk, and to derive gk from fx is called the Fourier transform. And in this case, we establish the connection between the original image, which is in so-called the real space, and the Fourier image, which is in a frequency space. This is a very, very simple example. Now, let's give you a slightly more complicated image to show you how you can read the Fourier space information. We're looking at the Fourier transform of an image of Fourier himself. That's the Fourier transform of Fourier. And in this case, the original image has an x and a y coordinate. The Fourier space image has an kx and ky coordinate. And one very simple thing to think about is the things close to the origin will have very short k vector. And that's describing the no spatial frequency information. And things further away from the origin will describe the high spatial frequency information. just to illustrate that, if we take this image and we mask out the high spatial frequency information, and we inverse transforming back. So this is called the inverse Fourier transform. Well, we still see the image of Fourier, but at a much lower resolution. For example, here, the details of its clothes is completely lost. And this is because in our Fourier space, we mask out all the high spatial frequency information. We can do it the other way. We can mask out the no spatial frequency information and do the inverse Fourier transform. This is what we get. Well, we lose the overall image shape. We lose the overall shape of Fourier, but we do preserve these fine details in the clothes, these very sharp edges. So that's what we see if we only keep the high spatial frequency information out of the image. And that's one simple example of how you can read an image in a Fourier space. Okay, that's enough math. That's enough very abstract concepts. Why are we talking about Fourier transform? How is that related to microscopy? Okay, let's come to the very basics of image formation of a microscope. And the key element in the microscope is the objective. And you can think it as a lens. So it has the back focal plane, which is behind the objective, and the sample is placed at the front focal plane of this objective. And what a lens does for any parallel light from the back is going to focus it down to one point in the front focal plane or the sample plane. And if the angle of this parallel light has an angle of alpha to the optical axis, it's going to focus down to a point that x equals f times sine alpha. F is the focal length. This is basically the design of objective. So this is how the objective is designed for. Now, make it this simple, we only consider two light rays. And the question we ask is that at the back focal plane, because this is what light come in, we have some light intensity distribution. Say, at a distance of k from the center of the objective, we're going to have some light intensity of A as a function of k. Now, what's the light intensity in the sample plane when it's focused down with all these different light rays? We can calculate that. Now, two light rays are going to propagate from the back focal plane all the way to the sample. And they go through two different paths. And there are two different lengths to this path. To calculate the distance difference of these two light rays to get to the sample, we simply draw a perpendicular line through the center of the back focal plane. And in this case, this distance d will tell you how much extra length this light ray has traveled to get to the sample. And to this distance d, we can calculate it very easily, assuming refractive index is 1, that's in air. And using very simple triangular mathematics, d equals k times sine of this angle alpha. And we know here x equals f times sine alpha. We can plug that back in. We get d equals kx over f, which is the focal length of the objective. So what does extra distance mean? Light propagates as waves from this plane all the way to the sample. And then these two waves, or many waves, can add together. One wave here, another wave has traveled some extra distance, so there's some phase delay. And light is also a sine wave, so we can write that in. So the intensity here at the sample I is going to be a sum of the intensity over the back focal plane times the effect of different phase delays, and that is a sine function. So we get here is sum of ak times sine of d, that's the delay, over 2 pi lambda. Lambda is the focal length of the light. And then we can plug in what we get from d. Here is inside the sine function, we have kx times kx over 2 pi lambda f. If you look at this appears similar. And if you still remember the mathematical formula I showed before, which I said is very important, you can see this is exactly a Fourier transform. That's what a lens does. It takes the image at its front focal plane and produce a Fourier transform of the image at the back focal plane. And that's why Fourier transform is so tightly associated to microscopy. Indeed, if we take an image of a Fourier, put it at the sample plane of the microscope, at the back focal plane, we will observe exactly the same thing as we have mathematically calculated here, the Fourier transform of Fourier. And this means a lot to microscope image formation. For example, as what we have discussed, in the Fourier space towards the center, that's where the no spatial frequency information is. Towards the edge, that's the high spatial frequency. And high spatial frequency means very fine features. On the other hand, well, microscope objective cannot be infinitely large. Here, we're talking about some real space in the Fourier, in the back focal plane. And so it has only some finite size of the back aperture. This means no spatial frequency information within this back aperture will be able to go through the objective and reach our camera and get detected. But high spatial frequency information outside of this back aperture will get cut off by the objective. And this is essentially the fundamental reason why microscopes have finite spatial resolution. You cannot resolve anything infinitely sharp. Let's be more quantitative. The size of the back aperture determines some maximum K value the objective will allow to go through. And this K value is related to the spatial frequency in the sample domain in this formula. K, spatial frequency equals K over 2 pi lambda f, where f is the focal length, lambda is the wavelength of light. Okay. Then, what is the maximum value of K? Well, from the previous slide, we know that given a light ray that has an angle of alpha to the optical axis, the K will be f times sine alpha. And the maximum value of K will be determined by the maximum value of alpha, or how high an angle this light ray can be from the optical axis. And that is essentially described by the numerical aperture of this objective. So K max equals f times sine of maximum value of alpha. And sine of maximum value of alpha is exactly the numerical aperture of the objective. So K max equals f times numerical aperture. And then, what does this mean to resolution? Okay, now we're talking about resolving two sine waves. And one sine wave like that, another sine wave like this. And if we're not considering this periodicity, we just simply look at the two peaks. And you can think, one easy criteria is that to be able to resolve these two peaks, the sum of these two peaks needs to have a dip in the middle. And in this case, the maximum value of the second peak is going to fall at the exactly same point as the minimum value of the first peak. And then the two sine waves will have a phase difference of pi. We can plug that in here. The resolution is related to the maximum spatial frequency as pi over maximum spatial frequency. And then put all this number together, we got the resolution equals lambda over 2 times NA. This is exactly what we have seen a lot of times in the microscopy literature, how the numerical aperture of the objective is connected to the resolution of the objective. We can also understand it in this way. Now, we think about the microscope objective focusing the light. Then we have our circular numerical aperture is completely filled by light. And that is going to converge down to one single point. And by definition, these points, or this focal point, is the points of function of the microscope objective. And now we also know that from the left side and the right side, the connectionship is Fourier transform. So it means that the Fourier transform of the light intensity and, of course, the phase at the back aperture is the points of function of the microscope. So that's the lecture. We talked about real space, and that's connected to the frequency space through the Fourier transform. And in microscopy, this Fourier transform is done by the objective itself, connecting the sample plane and the back focal plane.